Assalamualaikum and good day to all of you. We are now going into the final section of chapter 6, 6.6 Convolution. Now convolution is another mathematical operation in Laplace transform that can be used to solve differential equations. Convolution. Let us consider two functions, f of t and g of t, and let f of t and g of t be piecewise continuous functions for t larger than or equals to 0. The convolution of f of t and g of t, which is denoted by this expression, so we write f of t, use the symbol asterisk, g of t. So this denotes convolution, is defined by the following integral. So the convolution of f of t and g of t is equals to the integration from 0 to t f of tau g of t minus tau d tau. So this is the definition of convolution. And notice that f is a function in terms of t, g is also a function in terms of t. But in the integrand, f is now expressed in terms of the variable tau, and g is expressed in terms of the variable t minus tau, and the integration is evaluated from 0 to t with respect to tau. So this is the definition of convolution. So for convenience, instead of writing f of t asterisk g of t to denote convolution, we can simply drop the t, we write f asterisk g. The convolution of two functions is commutative, that is, the convolution of fg is the same as the convolution of gf. So f asterisk g is the same as g asterisk f. So we can rewrite this expression in the following form. We can also write g of t asterisk f of t, that is the convolution of g and f, is equal to the integral from 0 to t g of tau f of t minus tau with respect to tau. So for the function g, the t has been replaced by tau, and for the function f, the t has been replaced by t minus tau. So f asterisk g is the same as g asterisk f. The convolution of f and g is the same as the convolution of g and f. That means when we evaluate these two integrals, the result should be the same. In this example, we are going to learn how to find the convolution of two functions. In particular, find the convolution of t sine t. So remember, this expression denotes the convolution of the two given functions. So to start with, let us refer to the definition of convolution. The convolution of f and g is equal to the integration from 0 to t f of tau g of t minus tau d tau. So firstly, you have to identify which of these two functions you want to label as f of t and which you want to label as g of t. For this illustration, I'm going to assign t as f of t, and I assign sine t as g of t. So t asterisk sine t. So this is f and this is g. According to the definition, for the function f, the t will be replaced by tau. So here, this is my function f. F of t is equal to t, so t now will be replaced by tau. Whereas for the function g, in the definition of convolution, g is initially expressed in terms of t, but in this integrand, g is expressed in terms of t minus tau. So in the question, the g of t is sine t. Now the t will be replaced by t minus tau. That means sine t becomes sine t minus tau. So this is the f of tau, g of t minus tau. So evaluate this integrand with respect to tau for 0 until t. So let us evaluate this integral. Now remember, when we evaluate the integral with respect to tau, t is considered as a constant. So we're going to use integration by parts. Where we let u equals to tau. This is the u and this should be the dv. So dv equal to sine t minus tau d tau. Now in order for us to use the integration by parts, we need to evaluate du. So if u equals to tau, du equals to d tau, and v will be the integration of sine t minus tau with respect to tau. Now integration of sine is negative cos, so we get integration of sine t minus tau will be negative cos t minus tau divided by negative 1. Now why do you divide by negative 1? Due to the method of integration by substitution, where we let u equals to t minus tau. Okay, and so the final answer for this integration is positive cos t minus tau. So apply the formula for integration by parts. U multiplied by v, that will be tau cos t minus tau, minus the integration of v du. So minus integration of cos t minus tau d tau. Continue. Okay, let us evaluate this integral. So you get tau cos t minus tau for the first term. Now integration of cos is positive sign. Okay, so cos t minus tau, when you integrate, you get sine t minus tau divided by negative 1. Now why do you divide by negative 1? By the technique of integration by substitution, where we let u equals to t minus tau. Now remember, this is a definite integral. Once we have formed this expression, we need to consider the two limits of integration, 0 and t. Okay, now since tau is the variable, therefore we need to replace tau firstly by t and then replace tau by 0. Okay, so the first step, replace tau by t, we'll get t cos, now t minus t is 0, so cos 0, minus minus is plus, sine t minus t, sine 0. Okay, so this is the first term when tau has been replaced by t, minus the second term where tau now should be replaced by 0. So we get 0 multiplied by anything is 0, minus minus is plus, sine t minus 0 is the same as sine t. Okay, now simplify all this. Sine 0 is 0, cos 0 is 1. So the answer becomes t minus sine t. Okay, so we see here that for the convolution of the two functions t sine t, the result is equals to t minus sine t. Let us now discuss the convolution theorem. If f of t and g of t are piecewise continuous functions on t larger than or equal to 0 and they are of exponential order, then according to the convolution theorem, the Laplace transform of the convolution of f and g is equals to the Laplace transform of f of t multiplied with the Laplace transform of g of t. But we know that the Laplace transform of f of t is equals to f of s, and the Laplace transform of g of t is equals to g of s. So in other words, the Laplace transform of the convolution of f and g is a product of f of s and g of s. Now let us look back at the definition of convolution. By definition, the convolution of f and g is equal to the integration from 0 to t f of tau g of t minus tau d tau. So if we want to evaluate the Laplace transform of the convolution of f and g, if we apply the definition, it means that we have to evaluate the Laplace transform of this integral. But the evaluation of this integral may be quite complex, especially when it involves integration by parts, and what more if the integration by parts needs to be performed more than once. So the convolution theorem says that we can skip this step. Instead, to find the Laplace transform of the convolution of f and g, we can simply get the Laplace transform of f of t multiplied with the Laplace transform of g of t. Okay, so this is a shortcut way. We don't have to evaluate the Laplace transform of this integral. Okay, now since these two are equal, right, therefore these two must also be equal. So if you want to find the Laplace transform of the integration from 0 to t f of tau g of t minus tau d tau, we can also get the result by finding the Laplace transform of f of t multiplied by the Laplace transform of g of t. In this table of Laplace transform, we can get the formula for the Laplace transform of the convolution of two functions by referring to formula number 25. Okay, so we will read here that the Laplace transform of the integration from 0 to t f of tau g of t minus tau d tau is equals to f of s multiplied by g of s. By the convolution theorem, the Laplace transform of f of t as strict g of t is equal to the Laplace transform of f of t multiplied by the Laplace transform of g of t. But we know that these two are equal and these two are also equal. So in other words, all these are equal to one another. Hence, if we want to find the Laplace transform of this integral, it is suffice to find the Laplace transform of f of t multiplied by the Laplace transform of g of t. So based on our previous discussion, it seems that the process of finding the Laplace transform of f of t as strict g of t is the same as the process of finding the Laplace transform of the integral from 0 to t f of tau g of t minus tau d tau, because these two are the same by definition of convolution. In other words, if we want to find the Laplace transform of either one of these, it is sufficient to get the Laplace transform of f of t and the Laplace transform of g of t and multiply both of them together. Okay, example. What is the Laplace transform of the convolution of t cubed and e to the power of 4t? So using this formula, okay, you can label one of them as the f and the other as the g, but actually it doesn't matter which one is f, which one is g, because what we know is that f as strict g is the same as g as strict f. Alright, now let us apply the formula. Laplace transform of t cubed as strict e to the power of 4t is the same as Laplace transform of t cubed multiplied by the Laplace transform of e to the power of 4t. So refer to the table of Laplace transform. Transform of t cubed is given by 3 factorial divided by s to the power of 4. Laplace transform of e to the power of 4t is given by 1 over s minus 4. And that is equal to 6 divided by s to the 4th multiplied by s minus 4. Question B. Laplace transform of 2 sin t as strict cos 6t. This is the same as finding the Laplace transform of 2 sin t multiplied with the Laplace transform of cos 6t. And we know that Laplace transform of 2 sin t is the same as 2 divided by s squared plus 1. And Laplace transform of cos 6t is s divided by s squared plus 36. Or this is equals to 2s divided by s squared plus 1 multiplied by s squared plus 36. The next question, what is the Laplace transform of the convolution of the number 8 and the function t cos t? So this is equals to the Laplace transform of 8 multiplied by the Laplace transform of t cos t. So Laplace transform of 8 is 8 over s, and search from the table of Laplace transform the formula for Laplace transform of t cos t, and that is equals to s squared minus 1 divided by s squared plus 1, everything squared. Okay, so this is what we are getting for the Laplace transform of 8s3 t cos t. We'll let us do more questions. Part D. What is the Laplace transform of the integral from 0 to t tau to the power of 5 e to the power of negative 2 t minus tau d tau? So notice that the first function is expressed in terms of tau and the second function is expressed in terms of t minus tau. So based on formula number 25, for the first function which is expressed in terms of tau, the tau must be changed into a t. So tau to the power of 5 becomes t to the power of 5. Okay, so f of tau now becomes f of t. For the second function, the t minus tau must be changed into a t. So e to the negative 2 t minus tau becomes e to the power of negative 2 times t. Okay, so g of t minus tau becomes g of t. So at this step, both functions are now expressed in terms of t. The variable tau does not exist anymore. Find the Laplace transform of t to the power of 5. It is 5 factorial divided by s power of 6. Transform of e to the negative 2t is 1 over s plus 2. Next question, what is the Laplace transform of the integral from 0 to t for tau cos 7 t minus tau d tau? Okay, so the first function is for tau. It is expressed in terms of tau. The second function is cos 7 t minus tau. And this function is expressed in terms of t minus tau. Okay, use formula number 25. This is equal to the Laplace transform of 4t. Okay, tau in the first function has been changed into a t. multiplied by the Laplace transform of cos 7t. The t minus tau in the second function is replaced by a t. Okay, so Laplace transform of 4t is 4 over s squared. Laplace transform of cos 7t based on formula number 8 in the table of Laplace transform, it is s divided by s squared minus 49. And simplify, we can cancel this s. So the answer will be 4 divided by s multiplied by s squared minus 49. Next question, what is the Laplace transform of the integral from 0 to t minus tau squared sinh 2 tau d tau? So this time the first function is expressed in terms of t minus tau and the second function is expressed in terms of tau. Okay, so remember f asterisk g is the same as g asterisk f. Alright, so based on formula number 25, whether the function is expressed in terms of tau or t minus tau, both tau and t minus tau must be replaced by t. Okay, so for the first function, t minus tau squared, it becomes t squared. Alright, so for the second function, sinh 2 tau becomes sinh 2t. So the Laplace transform of this given integral is equal to the Laplace transform of t squared multiplied by Laplace transform of sinh 2t, and continue to get the Laplace transform of each of these. So the answer is 2 over s cubed multiplied by 2 over s squared minus 4. Question part G. What is the Laplace transform of the integral from 0 to t negative 3 tau sin tau d tau? Notice that this whole function is expressed in terms of tau, so we can regard it as the function f of tau. And there is no function expressed in terms of t minus tau, therefore we say that g of t minus tau is just the constant 1. Okay, so let us apply formula number 25. Remember, for formula number 25, the tau must be changed into a t. That means the Laplace transform of this given integral is equal to the Laplace transform of negative 3t sin t. Okay, so the tau in the first function has been replaced by a t, and the second function, since it's just a constant 1, so we write here Laplace transform of 1. Okay, now Laplace transform of negative 3t sin t based on formula number 15 in the table of Laplace transform, where we take k as equals to 1. So the answer will be negative 3 multiplied by 2s divided by s squared plus 1, everything squared. And Laplace transform of 1 is 1 over s. Cancelling these two s, the result is equal to negative 6 divided by s squared plus 1, everything squared. Okay, so notice that here we are evaluating the Laplace transform of an integral where the integrand is a function in terms of tau alone. So let's say this is f of tau, and so we notice that the result is as follows. The Laplace transform of the integral from 0 to t f of tau d tau is the Laplace transform of f of t, so this is Laplace transform of f of t, which is f of s multiplied by 1 over s. In other words, it is f of s divided by s. Okay, so in general, the Laplace transform of the integral from 0 to t f of tau d tau is equals to f of s divided by s. Second question. What is the Laplace transform of the integral from 0 to t e to the negative 3 multiplied by t minus tau cos 5 t minus tau d tau? In this problem, the whole function is expressed in terms of t minus tau. Okay, so all of this is the g of t minus tau, whereas there is no function expressed in terms of tau. That means f of tau must be just the number 1. So apply formula number 25. This Laplace transform of this integral will be equals to the Laplace transform of 1 multiplied by the Laplace transform of this function where the t minus tau has been changed into a t. Okay, so Laplace transform of e to the power of negative 3t, take note t minus tau has becomes a t, cos 5t, again this t minus tau has been changed into a t. Now continue to get the Laplace transform of each of these functions. Laplace transform as we know is Laplace transform of 1 as we know is 1 over s, and Laplace transform of e to the negative 3t cos 5t using formula number 14, okay, where a is equals to negative 3. So we write s plus 3 divided by s plus 3 everything squared minus 25, where k is equals to 5. Okay, So this is the answer for the Laplace transform of the given integral. So we can say that if the whole function is expressed in terms of t minus tau in the integrand, so to get its Laplace transform, the answer is g of s divided by s. Okay, so this is the Laplace transform of the function g, which is given by g of s and multiplied by 1 over s, that is divided by s. Next problem, what is the Laplace transform of the integral from 0 to t, 3 of t minus tau, tau to the power of 4, e to the 2 times t minus tau, d tau. Okay, now this time notice that the integrand is arranged in such a way that the function in terms of t minus tau and the function in terms of tau are quite mixed up here. Okay, so we can rearrange. This will be considered as the function in terms of tau, and the product of these two is considered as a function in terms of t minus tau. So the result will be as follows. The Laplace transform of this given integral is equals to, for the function expressed in terms of tau, the tau to the power of 4 becomes t to the power of 4, whereas the function in terms of t minus tau, 3 times t minus tau multiplied by e to the power of 2 times t minus tau becomes 3t e to the power of 2t. Okay, so the t minus tau becomes a t. The t minus tau for the exponential function also becomes a t. Now find the Laplace transform for each of these functions. Laplace transform of t power of 4 is 4 factorial divided by s power of 5, and Laplace transform of 3t e to the power of 2t based on formula number 9, we get the answer as 3 divided by s minus 2 everything squared. Okay. Our next interest is to solve integral and integral differential equations. The convolution theorem that we have just learned is useful in solving equations involving the Laplace transforms of integrals in which an unknown function appears in the integrand. So examples are the integral equation and the integral differential equation. Okay, so after this we are going to learn how to solve integral and integral differential equations by using the method of Laplace transforms, where we need to apply the convolution theorem. Example, use the Laplace transform to solve the integral equation f of t is equals to 2 minus 4 times the integration from 0 to t sine of tau f of t minus tau d tau. Okay, notice that in this equation there is an integral, and therefore we call this type of equation in general as an integral equation. And f is the unknown function, and f appears in the integrand. So we are going to solve this equation by using the method of Laplace transform. So here's the solution. We are going to start by finding the Laplace transform of the left side as well as all the terms on the right side of the equation. So we find the Laplace transform of f of t, which is equal to the Laplace transform of 2 minus 4 times the Laplace transform of this given integral. Now we know that the Laplace transform of f of t is just f of s. Laplace transform of 2 is 2 over s minus 4 times. Now the Laplace transform of this integral can be found by using the convolution theorem. Okay, for the function sine tau, the tau will be changed into a t, so sine tau becomes sine t. And for the function f of t minus tau, the t minus tau will be changed into a t, therefore f of t minus tau becomes f of t. So in other words, the Laplace transform of this given integral is equal to the Laplace transform of sine t multiplied by the Laplace transform of f of t. Laplace transform of sine t is 1 over s squared plus 1, and Laplace transform of f of t is f of s. Now at this step, fs appears on the left side and also on the right side. So we are going to shift the function with the fs on the right side to the left. So we get the following: f of s plus 4 divided by s squared plus 1 f of s, and on the right side there's a single term 2 over s. Now fs appears in these two terms, so we're going to factor the fs. So inside this bracket we write down the coefficients of each of these fs. So we write 1 plus 4 divided by s squared plus 1, f of s is equals to 2 over s. And notice that this coefficient of fs is a sum of two rational functions. So we're going to make this into a single quotient. as follows. So you write s squared plus 1 plus 4 divided by s squared plus 1 multiplied by f of s is equals to 2 over s. And we simplify the numerator to get s squared plus 5. And therefore, the coefficient of f of s is s squared plus 5 divided by s squared plus 1. To continue solving this equation, we need to make sure that the coefficient of f of s is equals to 1, and that can be done by dividing the whole equation by this quotient. Okay, so on the right side, we get 2 over s multiplied by the reciprocal of this rational function. So f of s is equal to 2 times s squared plus 1 divided by s times s squared plus 5. To get f of t, remember f of t is the unknown function. This is what our aim is to know what f of t is. We can get it by writing down the inverse or finding the inverse of the function f of s. Okay, so inverse of 2 times s squared plus 1 divided by s times s squared plus 5. Let us continue with our work. We want to find f of t, which is the inverse Laplace transform of 2 times s squared plus 1 divided by s times s squared plus 5. Now this is a rational function and the denominator contains a product of two factors. So we are going to decompose this into a sum of two partial fractions to get the inverse Laplace transform. Okay, so this is the work of the partial fraction. Okay, so for the first factor at the denominator, which is s, the corresponding partial fraction is in the form of a over s. Okay, because this is s of degree 1 and therefore the numerator is just a constant. For the second factor at the denominator of this rational function, it is s squared plus 5. It is a quadratic factor and therefore the numerator for this rational function is a linear factor. We write it in the form of bs plus c. Now we are going to find a, b and c. To do that, we firstly take the common denominator between these two factors. So we'll get the numerator now is a times s squared plus 5 plus bs plus c times s divided by s times s squared plus 5. Now the left side is equal to the right side, meaning that the left numerator must be equal to the right numerator. So expanding the right numerator, we get as squared plus 5a plus bs squared plus cs. Expanding the numerator on the left, we get 2s squared plus 2. Compare the left side with the right side. So we can firstly group the terms with the common factor. In this case, there are two terms with common factor s squared. So we factor the s squared, so we get a plus b times s squared plus the rest of the terms. Compare the left side with the right side. Firstly, let us compare the coefficient of s. On the left side, the coefficient of s is a c. On the right side, there is no coefficient of s. That means c must be equal to 0. Now let us compare constant terms. On the left side, the constant term is the 5a. On the right side is 2. So a must be equal to 2 over 5. And then comparing the coefficient of s squared. On the left, the coefficient of s squared is a plus b. On the right side, the coefficient of s squared is equal to 2. Now we already know the value for the a, and therefore we can find the b. Now b is found to be 8 over 5. So substitute a, b, c back into this form of partial fraction. So we get the following. Okay, now a is given as 2 over 5. So a is 2 over 5. So we write 2 up here and 5 down here. So 2 over 5s plus. Now b is found to be 8 over 5. So 8 over 5 times s. 8 over 5 times s plus c is 0 divided by s squared plus 5. Let us transfer the result back into this problem of finding the inverse Laplace transform. So we write f of t is equal to the inverse Laplace transform of 2 over 5s. Okay, and 8 over 5 times s, we can put 8 at the numerator and 5 we put it at the denominator. So we write 8s divided by 5 times s squared plus 5, and this number 0 here can be disregarded. Okay, continue. Get the inverse Laplace transform of each of these functions. You can split this into two parts based on the linearity of the inverse Laplace transform. So we write inverse Laplace transform of 2 over 5s plus 8 over 5 inverse Laplace transform of s divided by s squared plus 5. And so finally we get the answer as f of t is equal to 2 over 5 plus 8 over 5 cos square root of 5t. So this is the solution of the integral equation. In this example, we are going to use the method of Laplace transform to solve the integral differential equation, which is given by dy dt plus 12y of t plus 36 times the integration from 0 to t y of tau d tau equals to 7, y of 0 equals to 0. So this is the differential equation accompanied by an initial condition, and therefore this whole set of problem is known as an initial value problem. Now for the differential equation, it involves a derivative as well as an integral. So in general, we call this type of equation as an integral differential equation. And in this equation, y is the unknown function. Y also appears in the integrand. So we are going to solve this integral differential equation by using the method of Laplace transform. So here's the solution. We begin by finding the Laplace transform of each term on each side of the equation. So find the Laplace transform of y prime plus 12 times the Laplace transform of y plus 36 times the Laplace transform of the integration from 0 to t y of tau d tau equals to the Laplace transform of 7. Now how to find the Laplace transform of this integral? We are going to use the convolution theorem. Now we have already solved a problem in the previous slide, and we found out that the Laplace transform of the integral from 0 to t f of tau d tau is equals to f of s over s. So we're going to apply this result to get the Laplace transform of the integration from 0 to t y of tau d tau. Okay, now let us continue. Laplace transform of y prime, as we know from previous lesson, it is s ys minus y of 0 plus 12 times, now Laplace transform of y is ys, plus 36 times, okay, now Laplace transform of this integral using this result is equals to capital Y of s divided by s, okay, where the f now has been changed into y. And on the right side, transform of s is just 7 over s. Now we can start apply the initial condition. Notice that y of 0 is given by 0, so this term gone to 0. And there are three terms which involve the common function y of s. So let us factor the y of s, and inside this bracket, we write down the coefficient of each of the ys on the left side of the equation. So it becomes s plus 12 plus 36 over s. Okay, now the coefficient of this ys can be made into a single quotient as follows. So be s squared plus 12s plus 36 divided by s multiplied by y over s multiplied by y of s is equal to 7 over s. So therefore ys must be 7 over s multiplied by the reciprocal of this quotient. Okay, 7 over s multiplied by s divided by s squared plus 12s plus 36. Now these two s cancel. That means y of s is 7 divided by s squared plus 12s plus 36. Now our aim is to find y of t, which can be determined by writing down or finding the inverse of 7 divided by the quadratic factor, which can be factorized. Okay, now s squared plus 12s plus 36, when you factorize, you get s plus 6 everything squared. Look at the table of Laplace transform. We get the result for the y of t. Y of t is 7t e to the power of negative 6t. Okay, so this is the solution for the given integral differential equation. Before I end today's lesson, let me make some remarks with regards to some mistakes that students used to do related to the convolution theorem. Okay. Now, Laplace transform of the convolution of f and g is equal to the Laplace transform of f multiplied by the Laplace transform of g. Okay, now this is based on the convolution theorem. Now remember, f asterisk g, or the convolution of f and g, is not the same as the product of f and g. In other words, the Laplace transform of f multiplied by g is not equals to the Laplace transform of f multiplied by the Laplace transform of g. We cannot apply the convolution theorem to find the Laplace transform of the product of these two functions. Example, Laplace transform of t asterisk sin t. Okay, now this symbol means convolution. The Laplace transform of the convolution of t sine t based on the convolution theorem is the Laplace transform of t multiplied by the Laplace transform of sine t, which is equals to 1 over s squared times 1 over s squared plus 1. Take note that t sine t is not the same as t asterisk sine t. This is a product of two functions, t and sine t, whereas this is a convolution of t and sine t. To find the Laplace transform of t sine t, do not use the convolution theorem because it is not equal to the Laplace transform of t multiplied by the Laplace transform of sine t. So how do you find the Laplace transform of t sine t? We can simply refer to the table of Laplace transform, look at formula number 15. So the Laplace transform of t sine t, based on the given formula, it is 2s divided by s squared plus 1, everything squared. Okay, so remember, this part is correct. Do not, please remember that these two are not equal, and this one is correct. Okay, now let's move on to another example. Laplace transform of e to the t asterisk cos 4t. So here we can apply the convolution theorem because this means the convolution of two functions. So this is equal to Laplace transform of e to the power of 2t multiplied by Laplace transform of cos 4t. This is equals to 1 over s minus 2 multiplied by s divided by s squared plus 16. Now e to the power of 2t multiplied by cos 4t is not convolution. That means the Laplace transform of the product of these two is not equal to the Laplace transform of e to the power of 2t multiplied by Laplace transform of cos 4t. Okay, so how do you find the Laplace transform of this function? We get it by referring to formula number 12 in the table of Laplace transform. So the answer is s minus 2 divided by s minus 2 squared plus 16. So in formula number 12, a is equal to 2 and k is equal to 4. Alright, so this statement is correct. And take note that these two are not equal and this statement is correct. The last example, what is the Laplace transform of sine 2t asterisk cos 3t? When you see this symbol, it denotes convolution. So you can apply the convolution theorem. So the Laplace transform of the convolution of sine 2t and cos 3t is equal to the Laplace transform of sine 2t multiplied by the Laplace transform of cos 3t. So transform of sine 2t is 2 over s squared plus 4. Laplace transform of cos 3t is s over s squared plus 9. Take note that sine 2t cos 3t is not the same as the convolution of sine 2t cos 3t, and therefore it is not equals to, therefore the Laplace transform of the product of these two functions is not equal to the Laplace transform of the first function multiplied by the Laplace transform of the second function. Okay, so how do you find the Laplace transform of sine 2t cos 3t? In this case, we need to use trigonometric identity. Sine A cos B is equal to half of sine A plus B plus sine A minus B. Okay, so if A is 2t, B is 3t, so sine A plus B, 2t plus 3t gives 5t. Sine A minus B, 2t minus 3t is negative t. So we use trigonometric identity. So please refer to the table of trigonometric identity to get the trigonometric identity for this given function. And then we can continue. We know that sine of negative t is equal to negative sine t because a sine function is an odd function. So the Laplace transform of half sine 5t is half multiplied by 5 divided by s squared plus 25 minus 1 divided by s squared plus 1. So this is the result of the Laplace transform of the product of sine 2t and cos 3t. Okay, so that means this statement is true because this is a convolution. And take note that the Laplace transform of the product of these two functions is not equal to the Laplace transform of the first function multiplied by the Laplace transform of the second function. And for this part here, yes, this is true statement. The Laplace transform of this given function can be found by using the trigonometric identity. Okay, so I hope you understand the examples shown here, so do not repeat the mistakes that says the Laplace transform of a product of two functions is the same as the Laplace transform of the convolution of two functions. We have reached the end of section 6.6, and so this is the end of chapter 6. Thank you for your attention and all the best to you in differential equations.